All right. Well, thank you, everyone. Thank you, Sharon, for moderating. I wanted to talk about a new pier bridge project just started officially in June, I believe, on advanced guidelines for stability design of slender reinforced concrete bridge columns. Okay, so loading this way, not that way. Okay, but this is a project. I'm the PI, and co-PI is Mark Denovit from University of Tennessee. He's the assistant professor there, but very versed in stability. And we've worked on some projects before, and this pier bridge project came along, and I knew Mark was the right person to team up with based on his experience. I believe Mark's on the call or on the Zoom as well. Yeah, so okay, so project overview. We want to develop guidelines for the efficient design of RC bridge columns. All right, so we're probably familiar with the approximate like moment magnification methods, as well as refined second order, either inelastic or inelastic analyses. Okay, and the AASHTO methods have largely been adopted from building codes such as ACI. Okay, and while some analogies carry over from buildings to bridges, engineers on the design floor often make conservative assumptions to fill in the gaps. Okay, and you know how those assumptions can be quite conservative in some cases, and that's one of the things we want to address with this project. Okay, so we'll evaluate the AASHTO approximate method and refined methods using second order inelastic analysis, mostly in open seas, and also identify controlling parameters such as L over R, which is of course important for buildings, but also superstructure stiffness, which is kind of unique in a way for bridges, much larger. You can think of the superstructure as a big girder or a big beam and a frame, right? It's much stiffer than what you would find in the building. So some subtle gaps to fill in there. Okay, and then identify cases where approximate and refined methods deviate in predicting column strength for vertical loads. Okay, so it's broken up into 6 tasks. Task 1 is underway, literature review. We're collecting prior experimental tests for monotonically loaded slender columns, as well as columns subjected to long-term loading, creep, shrinkage, those types of effects. And so far, we've found about 500 experiments on slender and or long-term loading columns, and we'll put those into a database format, which I'll talk about towards the end of the presentation. And then also, just make sure we identify the background of current provisions within AASHTO, as well as the California amendments, and then best practices for second order inelastic modeling of reinforced concrete columns, and then models for long-term behavior of concrete. Okay. Task 2 is to look at individual column models as well as some bridge models. Okay, so by individual column models, we have the kind of canonical sway and non-sway members. You can look at a lot of behavior with these simple models with springs, for sway, and then different end moments, for non-sway frames and different parameters. You run over a bunch of different slenderness ratios, boundary conditions for the sway case, and then for the non-sway case, and then look at concrete strength, yield strength. We're pretty much locked in to 4,000 or 3,600 PSI, grade 60 steel. Look at confinement effects, cross-sectional shapes, circles, squares, and reinforcement ratios, as well as loading conditions, and then long-term load to total load. Okay, so we'll develop these models within OpenSeas and then set it up in a way where we can look at a wide variation of these parameters. Okay, and Mark and I met with Sharon on Friday, and we told her, oh yeah, we could do an easy off-the-shelf OpenSeas analysis in a couple hours. So I did that this weekend and did some OpenSeas analyses with circular reinforced concrete columns, just to kind of show you what types of analyses we're we're thinking of, with initially off-the-shelf components like fiber sections, co-rotational mesh of displacement-based elements. Looking at columns of length L, 3 foot diameter, 1.5% steel, let's say, and just looking at different slenderness ratios or L over D ratios from 5 to 40, and then just loading axially, and then looking at the capacity, and then as expected, as the slenderness increases, the column capacity decreases, and the kind of our best guess, as Mark says, using refined second order analysis, is giving us the results we would expect. The dashed line here is kind of the F prime C AG, crushing load, and then as the column gets more slender, we get down to lower axial load capacities. All right, this is for non-sway. I gave it a small out of straightness, to kind of trigger the buckling, but we're getting reasonable results, and that gives us a good starting point, for that task of looking at individual column models. Okay, and then also within task 2, we'll develop some simplified bridge models. I think I win the award for least sophisticated bridge drawing you've seen today. But kind of the basic idea here is we'll develop models with multi-span. All the 2 spans are shown here, multi-bends, 1 bend is shown here. But looking at vertical loading on the bents, and then how that transfers into the columns, or loads over the bents, how that transfers into the columns. Look at some loading eccentricities, different column heights, different column, setting everything up to run through different, span lengths, number of spans, single column, multi-column bents, and then also pinned and fixed conditions down at the bottom of the columns, and also abutment models. So, one of the big questions is, with seat type abutments, can the vertical loading induce sway to where we engage the sidewall or the back wall, and then how does that affect the overall strength of the columns under heavy vertical loading, or slender columns under moderate vertical loading. Okay, so in task 3, after developing the refined models in task 2, okay, we'll compare those models with the experimental database from task 1, and then extend these single column models out to long-term behavior. There's a couple of ways to do this in OpenSeas. One is through a relatively new addition from Gino Karama and his students and researchers from Notre Dame, this time-dependent concrete model, or TD concrete. And we can also use parameter updating of kind of basic concrete models using Python functions. All right, so like just modify the parameters of, say, concrete 01, and then look at the analysis as it marches through years of time, if you will. And then, of course, compare with the experimental database for the experiments that involved long-term loading. Okay, and then develop the OpenSeas models for bridges and extend the bridge models to long-term behavior as well. Okay, and then get into automating all this. Look at the many cases need to be examined, and then compare the results with current AASHTO guidelines to ensure flexibility and evaluate different variations and modifications to the design methodology. Okay, and then run parametric studies evaluating selected cases and analyze data to quantify the accuracy and identify shortcomings. Okay, so what are we going to get out of this? One such thing, this is something that some work Mark has done from the buildings world, all right, but we'll develop similar type interaction diagrams for columns, right, where we have like, this is from ACI, of course, again, from the buildings world, but we'll develop something similar based on AASHTO guidelines. Okay, this figure A here on the left, all right, shows the strength considering second order effects. Okay, and then the using different EI effective stiffnesses. The figure in the middle, the B, contains different strength calculations based on different effective stiffnesses and different design methodologies. And then the figure on the right is basically some open seas analyses, which show, sometimes the design methodology is conservative, sometimes it's unconservative, right? So if you look at, I think you can follow my mouse, right? Is say a case of 7 meganewton axial load and 100 kilonewton meter bending moment, we'd be right here, right? The refined or our best guess second order analysis says that's okay, right? But if you go to the same point on these design methodologies, they're outside the dashed lines, so it's not okay. All right. So the analysis is saying that the design methodology is too conservative. However, if you go to a case of, say, low axial load, say 1 meganewton, and high moment of, say, 450 kilonewton meters, say right here on figure C, right? It's not safe, but the design methodologies, right, are saying that that is pretty close to safe. Okay, so kind of drilling down and looking into these cases of where the design methodologies are too conservative or perhaps unconservative, or perhaps some deviation between design methodologies will be part of this evaluation. Okay, so and then from that, develop and verify design guidance. Okay, so any potential modifications to design based on effective stiffness, does this depend on axial load, effective length factors, and then design limitations for lateral displacements or deformation limits, and then just kind of loop back to task 4 and based on those guidelines, rerun the parametric studies, reanalyze the data. Okay, task 6. All right, the final task is develop final recommendations, and then also ensure that these types, the guidelines and analyses we develop with open seas can also be done on the design floor using, say, CSI Bridge. Okay, so we'll create bridge models in CSI Bridge and then analyze those models in the same way a design engineer would follow through design steps. Okay, just to ensure that the recommendations are actionable. Okay, kind of along the same lines as what Farzin was saying in the last presentation, make sure this gets into practice and something that can be done, right, on a day-to-day basis. Okay. And then kind of as a supplement, right, the experimental tests of Slender RC columns gathered in task 1 will put into a database like the steel concrete composite column database that Mark has maintained for his research in composite columns. And then, assess kind of as a supplemental task 7, let's say, assess how much it would take to kind of integrate the Slender RC column database that we're gathering in task 1 could be tacked on or integrated with the peer seismic performance database. Okay, although the full integration is beyond the current project scope, but just kind of seeing what different data fields would need to be added to the SPD is something that we'll explore and will help support future research within peer and outside of peer on Slender reinforced concrete columns. All right, so the peer SPD has about 400 columns experiments, but they're mostly non-slender. And a lot of the pictures we've seen today are aspect ratios of maybe 5 to 7 or so, but that's not the entire inventory. But we'd like to see if we can extend this out to more slender columns. Okay. And finally, thank you to Pierre. Thank you to Caltrans for the support. And I guess we'll see if there's time for, or it is time for questions. So I'll hand it back over to Sharon.
Thank you, Mike.